So, welcome to our seventh lecture. Can you believe it's seven already? Oh my God, time flying by. And in this lecture, we're kind of moving on to a totally different area of chemistry. So we're not going to be doing any more math, any more units. Well, not for a while, not forever. Don't get too excited. But in this chapter, we're going to mostly talk about atoms. So this lecture is going to have like three parts to it. First part, we're going to look at what's called Dalton's atomic theory. So Dalton was the guy who kind of came up with the idea that there are atoms, the world's made up of atoms. So we're going to talk about what he said. Then we're going to look at, well, if there are atoms, what the heck do they look like? So we'll talk about what atoms actually look like. And then finally, we're going to look at the way that we represent atoms. So that way that we represent atoms and what's inside of an atom, that's called atomic notation. So let's go ahead and get started looking at atoms. Okay, so what is an atom? So let's start off by just defining what I mean by that word. So if you look it up in the dictionary, if you want to know what the word atom means, they're going to tell you it's the smallest part of an element that maintains its chemical identity. It's the smallest part of an element that maintains its chemical identity. So what I mean by that is it's like the smallest piece of gold that's still gold, that looks like gold, that acts like gold, that has the same properties as gold. It's the smallest piece of, I don't know, carbon, that looks like carbon, that acts like carbon, that still has all the properties of carbon. So there are parts of the world that are smaller than atoms. Those are called subatomic particles. And we're going to actually talk about that in this chapter that we're currently working on. All right, but for an atom, it's the smallest piece of something that's still that something. All right, so this idea that the world's made up of atoms, it goes back actually quite a long time. And, even back to ancient Greece, people started thinking, well, maybe the world was made up of small particles. But the first kind of modernish definition of atoms and how atoms behave was developed by a guy by the name of John Dalton. So John Dalton, he lived in like the 1700s, I suppose, and he came up with the atomic theory. All right, so the atomic theory, it has four parts to it. And the main part of this video, we're going to go over those four parts. So let's go ahead and get into it. So what did he say, what is this, 400 years ago? What did he say about the way the world's put together? He said, first off, every element is composed of tiny indestructible particles called atoms. So another way of saying that is, he said, hey, yeah, the world is made up of atoms. Kind of the first guy to say that. All right, in modern times at least. The world is made up of atoms. All right. Second part of his theory, he said, not only that, all atoms of an element are identical. So every carbon atom is just like every other carbon atom. Every oxygen atom is just like every other oxygen atom. Now, it turns out that's not 100% true. We're going to see that there's a little bit of something not quite right about that statement, but it's pretty close to true. Every atom of an element is identical. We could expand that a little bit. We could say not only is every carbon atom like every other carbon atom, we could say that if you are different atoms of different elements are different. So a carbon atom is different than an oxygen atom. An oxygen atom is different than a nitrogen atom. A nitrogen atom is different than a hydrogen atom. All right, so if you're a different element, you behave differently. All right, all atoms of an element are identical. Atoms of different elements are different. All right, now there's two more parts to his theory. These two parts have to do more with like how atoms interact with each other. So let me flip over to the next slide and we'll talk about the last two statements in his theory. All right, so statement number 3 says atoms combine in simple whole number ratios to form molecules. Now molecules, those are basically the smallest particles of a compound. So atoms combine, and let's kind of focus in on the critical words here. combine in simple whole number ratios to form molecules. So the way that we represent those ratios, that's what a formula is. So we can represent how many atoms are getting together. We can represent them with formulas. Represent with formulas. So for example, let me show you a couple of molecules here. Molecules are just two different atoms put together. Now what Dalton said is they're always going to get together in a simple whole number ratio. So to start off with, this would be a molecule, all right? This would be a representation of a molecule. All right, so the colors are sort of always like standardized in any book or any biology book you look at. When you see a black sphere, that represents carbon. And when you see red spheres, the red ones, those are oxygens. So this entire unit here, made up of one carbon and two oxygens, that is a molecule. And I could write the formula based on it. One carbon and two oxygens. This is carbon dioxide. All right, I miswrote there. Let me erase that. Carbon dioxide. So carbon dioxide is a compound. Now, if we look at it, it has a makeup just like Dalton said. It's going to be atoms getting together, sure, I guess that's the word. Atoms getting together, and they always get together in a simple whole number ratio. So for every one carbon, for every one black dude, there's two red guys, two red spheres, okay? So that's what I mean by a simple whole number ratio. For every one carbon, and again, if there's not a subscript, it's a 1. For every one carbon, there's two oxygens. Or this would be another example. Another way carbon and oxygen get together is sometimes they join up like this. So they join up with one carbon, one black sphere, and one red sphere, one oxygen. So this is another compound. This would be called carbon dioxide, monoxide, I should say, carbon monoxide. All right. Atoms combine in simple whole number ratios to form compounds, to form molecules. So another way of saying this, you'll never see this. For every carbon, there is, I don't know, 1.765432 atoms of oxygen. You can never have some sort of like crazy decimal number of atoms. It's always got to be 1 for 2 or 2 to 1 or 1 for 1, something more like that. The main reason for that is you can't have some part of an atom. It's got to be like 1 atom or 2 atoms. You can't have 0.7654321 atoms. All right, simple whole number ratios. So there's a fourth part to its theory. Let's move on to that. His fourth part says, well, when we have these compounds or elements and they're around each other, they're going to react with each other. And when they react with each other, what's going on, atoms are not broken down in a chemical reaction or not changed into another type. So in a chemical reaction, atoms are not broken down or changed into another type. So for example, for hundreds of years, people try to take lead and turn it into gold. Can't do that. You can't take one kind of atom and make it another kind of atom. You can't take lead and make it gold. So all that happens in a chemical reaction is that atoms combine in some new way. They get together in some new way. Now, that's what this example is showing you down below. And in a future chapter, we're going to learn all about reactions. I just want to point out to you what Dalton realized was that anytime there's a reaction, the number of atoms is going to be staying the same. So we're not going to make atoms, we're not going to lose atoms, we're not going to change atoms from one thing to another, carbon to oxygen. So for example here, and again, all these colors are sort of standardized. The black sphere, that's a carbon. So there's one carbon on, I'll use my highlighter here. There's one carbon on this side, that would be this guy. There's one carbon on the other side when the reaction's over. This reaction is like burning natural gas. CH4 is methane. It's, if you have a gas stove in your house, that's what you're doing. And when you burn it, the carbon that is there from methane, from CH4, is still there at the end. It's just now joined up with different things. So when you burn, really what's going on is it's combining, reacting with oxygen. And in this case, we're starting off with 4 oxygen atoms, When the reaction's over, we still have 4 oxygen atoms. Can't make atoms, can't lose atoms. When you burn natural gas, methane, you start off with 4 hydrogens. The hydrogens are the white guys. You start off with 4 of them. When the reaction is over, you still have 4 of them. So all that happens when you burn natural gas is it reacts with oxygen. The atoms change who they're connected to, and then we end up making carbon dioxide actually and water. So new things are forming, new substances are forming. We're forming water, for example, but those atoms that we started with, they're still there. They've just joined up in a new pattern in a chemical reaction. All right, so that's it for Dalton's atomic theory. That's it for part A of this lecture. We'll move on and learn more about atoms in the next part.